Good morning. We are presenting SEW-3 today, and in this webinar we will be analyzing the data we have collected from two reference sites. One of them is actually in USA, Marshall, Texas, the other one in China. For your information, we have also recorded SEW-1 and SEW-2. Both webinars have been broken down into 4 chunks and put on YouTube, and you can watch it anytime you want. So let's move on. So what we hope to accomplish today is to show you how we have collected these data and then how we can predict the condition of the generator from this data. By the way, I want to remind you that vibrofiber, our sensor, can monitor both vibration and temperature. So today we will be looking at both the trend of the vibration change in amplitude and also the temperature of each end winding that the sensor has been attached. So the webinar will consist of 2 parts. The first part will talk about the Perky plant in Marshall, Texas, owned by AEW, and the second reference actually in China. We will see that the two plants are operating completely differently, and this will affect the expected life of the generator. We'll be talking more about that in a little bit. So first reference site, for those who has not attended SEW-2, I want to explain to you some of the facts about the generator. There is a very large generator, 775 megawatt, about 32 years old, made originally by Westinghouse, and is operating as a base load and is shown to be very constant. Now later on, when we talk about the China reference plant, and you will see a very drastic difference in the way they operate the plant. And by the way, what I hope to do is make this webinar a little bit more interactive. And in case you have any question, can you enter them into the chat box? And at the end of the webinar, I will have a question and answer period, and I would like to address these questions for you. So on the Perky plant, and here is the location where we have installed the sensor. Okay, you can see channel 1 on T6, channel 11, 12, 13, 14, 15, accordingly on T4, T1, T2, T5, T3. So when we will be following this order and addressing the location of the winding itself, because that is the purpose of TG Guide. So we are suggesting from the vibration amplitude there's a slight looseness developing, but it's nothing of major concern. So I like to summarize it first up front. On channel 6, 7, and 8, that the sensors are mounted on T16, T41, and T42 on the turbine end. They are showing a slightly increase in amplitude. Well, how do I compare? I take the minimum vibration amplitude and compare with the largest amplitude. Okay. Now, The sensor, before we ship them, they gone through a calibration test. We actually attach the shipment with a certificate of conformance. I will be able to show you such a certificate later on during the analyzing the China plant. Excited about here though, and all the data that we have collected show that they are well within, although they are showing some difference. Some showing very low amplitude of vibration, and then some showing slightly higher. But just to refresh all of us, the concept is we catch data first and then set it up as a reference, a baseline value. And then from there, we say we set an alert limit at 2 times that reference. So here, we set the baseline at 2 mil. By the way, that 2 mil is larger than most of the data you've seen today. Okay, so we are very conservative. And then the alarm should be set at 8 to 10 mil. Okay, that we suggest that we should shut down the machine and do some maintenance right away. So let's discuss first channel 1 to 8, and the y-axis is actually peak to peak in mil, and the x-axis is time. Okay, you can see during this time there are loading differences. The machine is going through cycles, and what it is when the loading decrease, the amplitude also follow. Okay, now to read the amplitude, the highest is therefore channel 7 and channel 8. You see, this is the grayish purple color, and followed by the blue. So there's max and min because of the loading difference. And in this case, only 2 are the highest, and whereas from the lowest to the highest can represent 2 times. So it is representing some degree of looseness comparatively. So in any case, if we were to pay attention in the future to this machine, of course 7 and 8 will be the first one we should pay attention to. But all in all, they are doing okay because they are well within the 2 mil, okay, at different loading cycles. Now then we look at the other sensors. One of them, by the way, channel 15, is very low, and then you can see on the high side you have channel 11 and 12. If you don't mind, I go back to the cross section here. Okay, now on the turbine end we actually install 7 sensors, and one of them was directly attached to the copper conductor T15. So I like to examine that for you, what the reading looks like, and that's channel 5. Okay, channel 5. So let's go back to the actual data. Oops, channel 5. So channel 5, as you can see, is light blue. Okay, and seems to be doing okay. So we place the sensor at the conductor itself, and it's showing is running well. Okay, so all in all, there is no question about the vibration amplitude in this Perky machine. Now, take a sample of the time domain waveform, and there you will see a frequency fast Fourier transform, and validating that the vibration signal is mainly 2 times line frequency is very clearly shown here. What is mysterious is that we have a different frequency distributed both on the low end and the high end. Now, they are not exactly harmonics either. Let's say the primary frequency is shown to be 120. Here there is a small harmonic at 240. But what about these little peaks? They are 30. Well, what about the 1x? We suspect that there is small vibration transmitted from the rotor, but we will be discussing more with the power plant about that. And of course, 120, 240, 360, there is a little bit of harmonics. Now, since we have already calibrated the sensor before we install, so these reflect differences, real differences, because when we do the calibration with a shaker, a programmable shaker, we don't see the harmonics. So these harmonics are generated from the actual vibration of the machine. And I was informed by experienced people that these vibrations might be induced by the whole base slightly rocking. This is a problem called the soft foot. And this is not a concern. The amount of these vibrations is small. I would like you to keep a mental picture of this, and then later on compare with China. We seem to have a lot of spurious vibration at different frequency in the China reference. So showing you the waterfall plot, and once again the main frequency is 120 Hertz. Now the harmonics are showing up in little sliver. Okay, not a big concern at all. So when we do our analysis, we show channel 4 and 7 that are slightly higher. Okay, but more importantly, the temperature are all different, and show a temperature 97 degree Fahrenheit, but that's okay. But it does compare quite differently with other sensors who's reading about half of that. Okay, so we're interested in investigating that with the plant engineer. It turns out that the SCADA system can read the water outlet temperature, and so we want to compare the two. Here are the details. Channel 7 and 8, as you can see, got up to 97 degree F. Now, it is not an alarming situation at all, because our concern is mainly the mica is temperature rated to 150. Now, we would not advise to run the generator at a temperature of 100 degrees C, not F. I mean, 100 degrees C will become 212 Fahrenheit. So this is comfortable. Now, the only thing that is curious is, look, the spread of temperature. Okay, you can see channel 8 has a low of less than 60 degrees, about 57, 58. Remember channel 5? Okay, channel 5 is where we put the sensor on the conductor, the copper conductor itself. That place, the temperature is also quite low. There is no heating problem here, but there is a spread of temperature values at different